All right, welcome back, everybody. Sorry we ran out of time. This will be a pretty short little lecture on thermal stresses and thermal expansion. So there's two parts of thermal. Um, One part is if it's free to expand, it will expand and it will create no thermal stresses. If it's not free to expand, like if it's locked down, pin, right? Not free to expand, then it produces thermal stresses. So we need to be able to calculate both. All right, before I do that, I want to talk about presentations. Those of you that presented, nice job. Those of you that didn't or weren't prepared, you have to start keeping track of things somehow. So week 2 on Thursday, this was talked about in class that you're going to present Tuesday 4/16. So everybody knew. It's just we're losing track of things because we're not keeping track. So you need a planner and you need to figure out how to use your planner and keep track of when things are due. I'm going to give you a 0 for not presenting. You can present on Thursday for half the points because now we're in week 3 and anything late is half credit. So hopefully you will do it and go for it. Graceland did have her presentation ready. She's taking this class online. So I thought, what the heck? Let's look at Graceland's. So I want to give her her due, right? Let's see if we can run it. Oh, she just did a PDF. All right, let's look at her PDF. She had elasticity and the pros and cons of stainless steel. So looks like elasticity is a physical property. It's the ability of a material or object to return to its original shape. So, and a rubber band, just like we talked about in class. So nice job nailing that one, Graceland. Some materials have high elasticity like rubber. If you take a rubber band and stretch it, it goes right back into its original shape. On the other hand, a ceramic bowl would be very low elasticity. So she's exactly right. And then stainless steel, pros and cons. Very clean, corrosion resistant, strong and durable, high melting point. Cons, low conductivity, so we don't use it for those. Can be easily dented and scratched. Pretty true, yep. It is expensive, and it shows dirt and grime. So there we go. She did it. So that's great. All right. Keep track of stuff, folks. Doggone it. All right, the calendar is here, and you do have a couple homeworks. 3 of them, 7, 8, and 10, all in thermal. So let's talk about that. I am actually going to use this thing and then just flip it around. So hang on, here we go. Oops, I don't know where it went. I'm going to turn it off. And I'm going to share the screen. And then we're going to use the... Oh, I closed it. Well, that's disappointing here. All right. The nice thing about thermal is it's pretty easy to work with. So this camera's not, though, is it? All right. Let's see if we can get a focus button. Come on, you can do it. There we go. So if you read about it, out of chapter 11, thermal stress and thermal elasticity or expansion. So they talk about it here, and they give you the 2 equations. And really, there's only 2 equations, but you got to understand that there's 2 situations. A situation where if it's free to expand, then the change in length is going to be alpha L delta T. So L is the original length, delta T is the temperature change, and alpha is a material property, the thermal coefficient of expansion of a material. So if we have steel, we look it up. If we have copper, we look it up. If we have whatever, we look it up. Notice the expansion, this is very interesting, has nothing to do with the cross section. So cross section does not come into here. But if it's free to expand, we can calculate that. And there are no thermal stresses. This is thermal stress, but if it's free to expand, no internal stresses are developed. If it's not free to expand, then we can calculate the stress. Very similar equation. Look at, they both have alpha, right? But this one is alpha L, and this one is alpha E, the modulus of elasticity, and they both have delta T. So if it's not free to expand, we can calculate the thermal stresses. So let's talk about this. If we have a, I'll use copper, a copper wire, and let's say it's 200 feet, and it is 0.2 in diameter, 0.2 inches, right? And we install it at 60 degrees F, right? But then winter comes and it goes to minus 10 degrees F. So when something gets colder, it wants to shrink. And this wire is between two telephone poles, and these telephone poles are not moving, right? So essentially it's fixed. Now we put sag in it just for this reason, because then the sag would come out when it shrinks. But we're not going to talk about that, but we want to talk about, like, okay, since it is locked down between two telephone poles, we're going to say it's not free to shrink, right? Let's say we didn't get much sag in it. All right, that'd be bad design, but let's just say that. So locked down between two telephone poles, that means that we do get, and I put a little TH next to my thermal stress. Alpha E delta T gives me that stress. Okay, so if there was no sag, we just went straight across, right? We could calculate this thermal stress. So I need to look up alpha for copper. So heading back to the back of the book here, and it looks like the coefficient of thermal expansion, that's this column. Notice the unit, inches per inch per degree Fahrenheit. So it's really just a per degree Fahrenheit. And it's to the -6. So copper down here is 9.3 10 to the -6. So we write that 9.3 times 10 to the -6 inches per inch per degree Fahrenheit. That's the unit, right? The elasticity, modulus of elasticity of copper is, we're going to use this only copper in the book, which is 15,000 KSI, 15,000, and I don't want kips, right? KSI, or I can leave it that way, either way. So I'll leave it, kips per inch squared, right? So whatever unit you put in here is the unit you're going to get out as stress, KSI. All right, and then the delta T. Delta T is going to be the difference between these. So 60 goes down to 0, that's 60 degrees, and then we go another 10. This is 70 degrees F. And we don't usually put a negative in there because it did drop 70 degrees. We just know that when things get colder, they want to shrink, right? So this is going to be a stress that is like it wants to shrink, but it's not allowing it to shrink, right? All right, let's see if we can crunch this number. (9.3) e to the -6. So that's how you put it in HP. Oh, you can't really see it. No, you can't see it at all, can you? Sorry about that. Anyway, 15,070. So I'm getting thermal stress of 9.765 KSI, or 90. 9769, whoops, 9765 PSI. Okay, and I know copper is stronger than that, so we're fine, but that's a lot of stress, right? That's a lot of stress. Copper, the cold drawn yield for copper is 40,000. 40,000 PSI is the yield. So it's fine, but it is getting quite a bit of stress from this big cool down, okay? And that's because it's not allowed to shrink. We pulled it tight, right? So in the real world situation, we don't pull it tight. We put a bunch of sag in there. And the reason we do that, so here's a better picture of it. And that's so this can go from this position to this position, right? So if it is free to expand, contract in this case, then we get no thermal stresses. But that means we get thermal shrink. Like we're going to get, and I put a little TH in front of this one too. And this one is alpha L delta T. So the same alpha, 9.3 times 10 to the -6, with the same unit, inches per inch per degree Fahrenheit. Its length was 200 feet. And I'm going to multiply by 12 to get it to inches. Right? Because it's going to be a small number, so I might as well get it to inches. And then I'm going to put my 70 degrees F in. If this thing is free to contract, then we can calculate it. 9.3 e to the -6 and 200 and then 70 times. It is going to contract. Oh, you really can't see it. Oh, there you can kind of see it. 1.562 inches. 1.562 inches smaller. So if we have that much sag in 200 feet, then we will not produce thermal stresses. All right, so that's it. Thermal's pretty easy, just these two equations, and you have to determine like, hey, it's free to expand, so we don't have any stresses, or hey, it's not free to expand, we can calculate thermal stresses. Either one. Equations are very similar, not too difficult, just keep your units straight. All right. Good job, everybody. See you all on Thursday.